Hello and welcome back to Calculus 3. So section 11.3 on the dot product. We talked about two-dimensional, three-dimensional vectors. I also mentioned could be any dimension on a vector. That's fine. So you can have an 8-dimensional vector. That just means you have 8 components inside. The vectors are essentially multi-dimensional numbers where you, for a 2D vector, right, you can think of it as a 2D number. It's not the same as a complex number. Complex number is a 2-dimensional number. But you can think of vectors as entities that could be numbers. And we've seen that we can scale them, right, multiply by a constant to change their length, their magnitude. And we've seen that we can add and subtract. The next order of business is to multiply vectors. We have 2 different ways to multiply vectors. One is called the dot product, which is this lecture, and the next lecture, 11.4, is the cross product. Those 2 together are the ways to multiply 2 vectors. Now, the dot product, which is the first one, is the extension of the one that you already know. When you say 3 times 5 is equal to 15, you are actually taking a vector that has only one component inside, which is 3, and so one-dimensional vector, and you are multiplying that by another one-dimensional vector, 5, and you are obtaining a scalar value, 15. The dot product is going to take 2 vectors of the same dimension, regardless what dimension it is. It could be 8-dimensional vectors. You can take 2 vectors, multiply them, and obtain a scalar quantity. So the dot product is generalization of multiplication. And the good old multiplication you learned in a 2nd grade or whatever is actually the part of the dot product where your input values are not vectors of dimension 2, 3, and on, but just one-dimensional numbers. So I like to start by a quick definition on how we compute the dot product for 2-dimensional vectors. So a vector u dotted with vector v is going to be a vector u which has u1, u2 components, dotted with vector v, v1, and v2 components to give us u1, v1 plus u2, v2. So this is the way to multiply. This is the definition. To multiply 2 vectors. Patience, young Padawans. So we have 3 times negative 2 plus 6 times 4 per definition up there. You okay?
Yeah, now we're good over here.
For the moment there. Negative 6 plus 24 is positive 18. So as we multiply 2 two-dimensional vectors, in this case 3, 6, and negative 2, 4, the product, the dot product of these 2 vectors is 18. Now, the dot product will be used in many concepts that are coming up in the course. And I will always point out the dot product. The dot product actually could be done between numbers, could be done between functions, and so on. So we'll use this dot product a lot in chapters 11 and 12. And then it will be back to 14. So 13 is the only chapter when we are actually not using the dot product. Now, the other definition of the dot product is related to the angle between 2 vectors. One of the big uses of the dot product is to find angle between 2 vectors. So if we look at yet another definition, we are going to say that given two non-zero vectors u and v, right? So given two non-zero vectors u and v, their dot product is given by, and now we write u dot v is equal to magnitude of u times magnitude of v times cosine of the angle between the two vectors. So I'll just write where theta is the angle between u and v. So this is what we have, and clearly, should I say clearly, we can use this formula to solve for theta and come up with the formula that will instantly calculate the angle between two vectors, and that is the dot product divided by the product of the magnitudes. This is, oh, sorry, inverse cosine. Holy nightmare. Wait. There is the inverse cosine in there. There we go. Much better. It's not better because now it's too cramped. I know you can do this in your notebooks. Tough luck. There we go. Now we can say theta equals inverse cosine. Perfect. So this formula here will be used to find the angle between two vectors. Now that's important, right? Because you might have two boats to pull onto a same, like two tugboats pull on the same tanker. They're going to come in at an angle, right? There are pulls and pushes and forces all over. Mechanical engineers, there's your formula to actually make your living. So there's a lot of forces that we have to compute. So this is going to work as an angle between two vectors. Now in 2D, in 3D, in 4D, because when you have two vectors, I don't care what dimension you're talking about, the two vectors will span a plane. Sheesh. So this realm over here is thru-dimensional, and I'm going to take no, actually let's go first with the two dimension. On the surface of the board or a wall or whatever, if you have two vectors drawn in any direction, there is angle between them, and the whole thing rests on the plane, which is the whiteboard. So these two vectors are on the two-dimensional surface. These are two-dimensional vectors on the two-dimensional surface, and that surface is a board, and then you have the vector in between them. Now what I'm going to do is I'm going to have two vectors in thru-dimensional space. Now I don't care which way you're going to have this way, this way, this way, whatever way you put them together. The fact is that these thru-dimensional vectors fit on a plane. And as you can see, it becomes a 2D angle in between. You see that? I don't care which way is this oriented and which way these two vectors work between. You will always be able to slide the plane, and then you will have the two-dimensional analog. This could be 8-dimensional space, where each vector has 8 dimensions on each of the terminal points. It doesn't matter. You still get to slide a 2D plane through those two vectors, no matter which way they're oriented, and get the angle, theta. So the dot product works in any dimension, in any dimensional space. Therefore, the formula to figure out the angle between those two works. Now, what doesn't work nice? When you have a 3D vector in a 3D environment to figure out what is the direction of that vector. There are ways, right? But it's not pretty. It's not easy as to say what is the angle with the positive x-axis. Because in a 3D space, your input is not positive x-axis. It is all of the xy plane. That is your domain. So it's much trickier to deal with those kind of things in 3D than in 2D. But the angle between two vectors is, as you can see, trivial, because it's always a two-dimensional concept, because it will always be the angle between two vectors which rests on the plane that those two vectors create. So, so we don't care about dimensionality in this particular case. Did it make any sense? At least for 3 people? Wow, terrible instructor, right? I know, I've been told. Labeled. All right, now, looking at this, at the red formula, the original formula up there, another concept should be clear. If two vectors that are given to you are non-zero vectors, that means that their magnitudes are not zero, right? So the only thing that could be zero is a cosine of an angle. So if the cosine of an angle, if the angle is 90 degrees, you get the 0 there. That means one of the famous theorems, if u dot v is equal to 0, then vector u is perpendicular to vector v. So two vectors are perpendicular. Now we say perpendicular for 2D, we say orthogonal to any of the higher dimensions. They're perpendicular, okay, 90 degrees between them. So any other theta will have dot product to be whatever other number. If theta is either 90 degrees or 270, which is equivalent to negative 90 degrees, that dot product would be 0. This is very helpful later on in our lectures. So I am actually going to box that as well, because this is one of the key points for today. So far we have 3 key points. Key point number 1, way to compute the dot product by multiplying their components and adding each one of those sets. And then to find the angle between two vectors of any dimension. And then finally, if the vectors are perpendicular, the dot product is 0, or the other way around. So that's a theorem on orthogonal vectors. We have some properties of the dot product. Property number 1, dot product is commutative. U dot v is the same as v dot u. Honors option. What's the proof for this? Right? Well, the proof, you can run either this calculation, where you will piggyback off commutative. One vector will be u1 times v1, the other vector will be v1 u1. Well, that's a scalar product, and you can assume, well, not assume, because we know that's commutative, so that's what you claim. The other way is to run this, where again u and v would be, so either way you do this, you will be playing with commutative rule with scalar, right, numbers that you learned in your grade school. Property number 2, C times U dot V. Right, this is associative property. So we can say it's right? C times U, C is a constant, right? There is no arrow above it. So when you have lowercase letter and no arrow, it's a constant, like number 7. And when you have the arrow, it's a vector. You just have to worry about dimension, but later. Dot product works on any dimension. So you can do that first and multiply that by V, or you can say U times C times V. So that's a little bit of community property there as well. 3, finally, the distributive property. So we have U dot V plus U dot W. So commutative, associative, and distributive properties all work for the dot product. Okay, so here's a problem for you to enjoy. Find the angle between vector u given as 3i plus 4j, and we put these little hats because these are unit vectors, and vector v given as 4j plus 5k. Find the angle between these two vectors. Bueno? 36.9 degrees? What happened?
60.
Yeah, degrees.
60.
What do you mean 60? 68? No.
60 degrees.
What do you have?
60 degrees.
60? So what did I do wrong? What do you have? 60?
It's not an apple.
Yeah, I know. Restarted. Oh, it's the user error. I typed in 16 instead of 41. I was just testing you. And you passed the test. Very good, very good.
So you got 16 by multiplying 3 times 0, right?
Yes.
Plus 4 times 4.
Yes.
Plus 0 times 4.
Yes. So any of those zeros kill those positions, and I technically only went to the 4 times 4 is 16, because the zeros will multiply and just kill across. All right, great. Now let's use this in the vector projection. So orthogonal projection. Orthogonal projection. Shadow. That's what it is. It's a shadow. So what do I have? If I have some line where I have vector v, and then I have vector u. If I shine a light perpendicular to this vector, what I'm going to get is a shadow, and this red shadow is a projection of vector u onto vector v. Clearly it's shorter and it has the direction of a vector v. So I don't care in which direction vector v goes, projection will go in the same direction. That's what's important. So we don't have to set this up on the horizontal surface and then you have vector u and a projection is also horizontal. No, it works on in any angle. As long as you shine the light perpendicular to the surface, perpendicular to vector v. So now, technically, what this projection is a component of vector v. If this was on a flat surface, you can claim that that is the x component of the vector u. I mean, vector u. Good effort. So now, formula for projection. Derivation is in the book if you're interested. I will explain what the parts of this formula are. So projection is given as u dot v divided by v dot v, all of that times v. Now these are magnitudes. So what do I have? If you look carefully at these magnitudes over here, this is v squared, so that's the magnitude. One of these, if you put the absolute value to get the magnitude, one of these will give you the unit vector. And the unit vector, it just tells you the direction in which you're going. And you see that the red vector has the direction of vector v. This, what I circled, is producing just the direction. The rest is the scaling factor that will shorten the vector u to be the right size as the light hits and creates this red shadow. So this is the formula. And we can use it. So let's go and project. So I'm just going to jump in the homework and pick up an example. No. Yes. So project vector u 5, 0, 15 onto vector v 0, 4, negative 2. Then let's do one at a time. I want to do backwards as well. I want to project v onto u as well. So both projections, u onto v and v onto u. Are you expecting the same answer? Okay, let's go.
I was talking to one of the Manitoba guys 4 years ago, Chad, that said just get one of those portable, different ones. Portable air conditioning unit. Do that. No, they actually have portable air conditioning units like a fridge. You bring them in, and then they drain into a tank. They clean empty. Yes.
Is it?
When you multiply -3 halves, 0, 4, -2.
Is this what we have?
6 is negative.
6 is negative. Yes, it is. Everyone good? Let's do same vectors, but projection of V onto U. Now we already know that the numerator up there is -30. That doesn't change. We will have vector U times U in denominator. So that's going to be 25 times, no, 25 plus 225 times vector U 5, 0, 15. So that's -30 divided by 250 times 5, 0, 15. We first cancel by 5. We have -3/5 times 103. And then we go and multiply, so -3/5, 0, and -9/5. I hope.
So you said that the second one, you have U dot V, and it's over U dot U.
U dot U dot U.
Times.
So every V is swapped with U. So the formula is completely opposite. Now we know that U dot V is the same as V dot U, so you can keep the same numerator. So if you are projecting onto V, it's all V's. If you are projecting onto U, it's all U's.
So the final answer, if the decimal as an answer, would that be accepted?
Yeah, sure. I don't want to upset you, like decimals, right? It's still numbers. How about some physics? Exactly. So work is defined as force times the distance. Force is a vector, distance is a vector, because you are going to go 5 meters that way or 5 meters that way. That has direction. So how much you go forward is the magnitude, and which direction you're going is going to be the direction. So now we have the formula for work, and we see that the work is a scalar quantity. Work is just a number given in joules as the unit. Now we are going to now expand our block. Right, remember the crate? So here's crate. It has its weight, has its normal force, and once we apply the force to it, it will give the friction. Now, friction is going to depend on the weight of the crate and the surfaces, if the wooden crate on the carpet or wooden crate on a concrete or wooden crate on ice. So the coefficient of friction will be different, and it will be either harder or easier to push the crate. The reason why the car is not sliding on the road is because the design for tires calls for the most amount of friction possible. Otherwise, there will be no grip, and you would not be driving safely. So, friction is not necessarily bad. Yes, it makes our pathetic technology regarding cars to be very inefficient, because the conventional gas-powered cars are about 25 to 27% efficient. That means that 3/4 of the money you pay into gas gets wasted towards friction, heat, and all of the other stuff that you don't need, and about 1/4 of that money goes to get you from A to B and run your air conditioning and music and whatever else you're running in a car. So now electric car, compare that to electric cars, about 90 to 95. Tesla car is about 90 to 95% efficient. So you see what kind of leap in technology we are making for leaving behind the gas-powered cars. Now, don't get into the argument that we are saving the environment with the electric car. We're not, because our state of energy right now is still pathetic, because we are still burning coal to make the electricity. So electric car is not environmentally friendlier at all. It's the same menace as the gas car, exactly the same thing. Once we figure out fusion, right, then you will have clean energy. You put hydrogen on one end and you have the water pumped out on the other end with all the electricity you want produced in between. Once we figure out fusion, then, I mean, commercially, fusion has been figured out for many years now, decades actually, but we can't make it commercially viable. So once that's figured out, to make it commercially viable, then the electric car would be the common sense, right? Right now, gas car, electric car, but so environmentally, it doesn't matter which one you have. However, if you look from efficiency standpoint, and if you look at the bang for the buck, right, 95% of what you put in the electric tank is used to get you places, and only 25% of what you put in a gas-powered car tank gets you places. So it makes sense financially to move to electric car, not as the environment, because, as I said, electricity in this country is, not this country, in this planet, is still mainly produced by burning coal or nuclear fission, which is, you don't know which one is worse. I mean, they're both equally bad. So now, talking about friction, friction in some cases helps, which is keep the car on the road, but in the same car, friction makes the inefficiency, right? So it's not necessarily good or evil concept. It arises when you multiply coefficient of friction by the normal force. The normal force is the one that opposes the weight force, and the weight force is the mass gravity. We talked about that. Mass is the quantification of the physical existence. So if the object or a person or whatever exists as in a physical realm, it will have mass. And mass is measured in grams or kilograms or so on. Does anyone know the unit for mass in the imperial system of units? Slug. There you go. Slug. So one slug is about 15 kilograms. That's the conversion factor. So yes, there is also unit of mass. Now, but in US, I mean, and England, pounds are used, which is actually unit of force. So, as I mentioned, you want to feel good about yourself, then you go and you measure your weight at the top of the Mount Everest when the moon is directly above you. And you are not lighter because you have to cut off all the fingers. You are lighter because of the gravity effects and things like that. I mean, no, you will be lighter because you have to cut off the fingers if you go there, but still. You get what I want to say. Anyway, so now, as you are pushing the object, if you want to use 100% of the force of the push, you better push parallel to the surface. Because that way, you are using 100% of the force to push the object. Which means that if I have to push the object that it's lower than me, right, then I would probably have to go down, because I want to push straight, parallel to the surface. All of the force of the push would be going into propelling the object forward. Now, if I push the object like this, which is what mostly happens, if you look at my vector over here of the force that it's pushing, clearly it has two components. A component that it's going downward and component that it's going forward. Each of those components individually are weaker than the length here. Now, the component that it's pushing downwards is actually making matters worse, because as I'm pushing like this, I am pushing down as well, making the weight of this table larger, making the normal force larger, making the friction bigger, and the friction is opposing my push. I'm not going to bury this object into the floor, so pushing like this is inefficient. I'm not saying you can't push things. Sure you can. You know, everyone pushes like this. You're not going to, go to the floor and push. But the trick is that if you want to use 100% of the force of the push, you will have to push parallel. As soon as you push at an angle, you will have to involve trig. This is your force of the push. You will have to involve the trig and figure out what is the actual force, which is the force in x direction. You will measure the angle at which you are pushing, and let's say that you are pushing with 100 newtons of force. That technically means that you're just very weak, okay? If you're pushing with 100 newtons. So you're pushing 100 newtons of force at 45-degree angle. Well, you have your force in x direction to be, you see that this is adjacent, so that's going to be 100 cosine 45. 100 cosine 45 is about 70 newtons. You are wasting 30 newtons, and actually you are contributing those 30 newtons towards friction, right, which opposes your push. Now, everyday dealings, you are pushing the chairs, you are pushing things that are easy to push, so that's not a big deal. If you are a laborer, well, you figure out, ways to make your life easier. But if you are a mechanical engineer and you are designing cranes and things, just go and watch some of those videos on YouTube. What happens when the angles are off when involved cranes, and you have plenty of examples when they're trying to take trucks out of ditches or loaders out of ditches or tractors out of ditches, and then they flip one or two cranes, right? Those truck crane things that they're trying to pull things, or when they're loading boats sideways into the river or a lake. as soon as insufficient engineering is and a thought is put into that kind of environment, things like this happen, and then disasters strike. So there is not much here for us to do, because you only have the distance you want to go, which is, let's say, 5, and you also have the force. The biggest problem for physics problems is to figure out the force. What is the actual amount of force that you are using? You might be as strong as you want. If you're not too smart, it's not going to benefit you great, because if you come at this desk at 98 degrees with, you know, with all of the might in the world, probably the only thing you're going to do is break the desk. All right, you're not going to move it far. So these are the things that that are there. So as soon as you are able to figure out the force that actually does the work, and throw away the vertical component, which is actually making everything worse, then in that case you are able to say, okay, the work is now going to be 100 cosine 45, and then times, I don't know, distance of 5 meters, and you will have the work that it's done. Now, why are we computing work? We're computing work because work is related to power. And in today's day of automation, we generally don't do the work. Most of the work is done by machines, which are run by electrical motors. And electrical motors have specs in power. Power is directly related to work. So if you're able to compute these things, you know what size, what power of the motor you need. Obviously, the more powerful the motor, the more money and more design goes into it. So you don't want to just, eyeball it there and say, yeah, it's going to be good, right? Which is usually in engineering precursor to all disasters that happen. So as engineer, your job is to figure out the force. Once you figure out the appropriate force, the rest is the simple dot product up there. You feed that in a dot product, you get your work. Once you have the work, you can convert that into power, and then you know what type of equipment you need. So let's get the number on this. Did anyone calculate this? Who's good? You like these things. What is the number over here? You're self-identified already. It's a 500 times cosine of 45, so it should be around. I'm sorry. 350. It's good enough. That's good enough, right? All right. Jules, done. Time for break. Yeah, to get some water and stuff, I know.